ערב טוב. ערב טוב, good evening. It's a real pleasure to open this special event, the Aero Lecture of the 26th School in Theoretical in Economy. And just to think that it's 26, it's really touching. Many of you, especially the students, have heard me just sharing some thoughts almost a week and a half ago, almost in the beginning, I mean exactly in the beginning of this school. I really said something, if you don't mind, I'll repeat about only on 2 points that I mentioned, because I see quite a lot of guests here that haven't been there. So 2 things that are really important to know is that this is a really, for the Israel Institute for Advanced Studies, one of the most important and significant stamp of our institute. And this is an occasion to present myself. I'm Michal Imyal. To those of you who do not know, I'm a biologist in training, a neuroscientist. And the one thing that happened to me, if you don't mind, in this week is that because I mentioned some thought about biology about a week and a half ago, I want to mention that through this week, many of you approach me and say, I have something for you. What about cell division if they divide not equally? And what kind of game the cells are? And you trapped me completely to these dynamic games. And I thank you for that. And I thank you for all your really clever questions. And I should admit, but that at night I tried to catch up. There was no way. No way. I tried really hard, but after 2 minutes, I mean, the lectures are recorded beautifully, but after 2 minutes, I thought it's beyond. So keep asking me about the biology, and I'll ask you about the economics. This is a fantastic dialogue. The last things that I want to say is really that it's a unique pleasure. The Aero lectures is really on behalf of of Kenneth Aero, that currently is not with us, but he's in Israel and is really enjoying the school. And he was really the founder, or one of the founder, I want to be exact, the founder? The director of this school, which is quite amazing. So it's really a great honor. And before we go to business, let me just introduce Eric Muskin, that is again took over to be the general director of this school. And I won't embarrass you too much, but I just want to say that I cannot even dream as a director of this institute of a better partner, really partner, for this adventure, because as you can see, I mean, everything is really relaxed, as if there is no work behind it. That's the best sign that everything is working very, very good, which means that a lot of work, but you don't have to know about it. Once somebody told me that on the stage, on the ballet, you don't need to see the sweat, but that means that there was a lot of sweat before. So thank you for all the work you put and the team around you. And I really thank you for that. And by that, I want to pass the microphone for you to introduce Drew, the speaker of tonight.
Okay. Well, thank you, Michal, and let me return the thanks, because I can't imagine a better and more welcoming environment for this summer school, which is now in its 26th year, than the Israel Institute for Advanced Studies. You mentioned ballet dancer as an image. I was thinking more of a duck who is gliding serenely along the water, but if you look underwater, the feet are madly paddling. And fortunately, I don't have to do that paddling myself, but there are plenty of people who are on our behalf. So this is now the 6th annual Arrow Lecture. The lecture was set up to honor Ken Arrow. And the idea is to bring a distinguished economist to Jerusalem at the time of the summer school and to talk about a topic which is of current theoretical interest, but also of interest to a wider public. And let me just tell you who the previous Arrow lecturers have been. It's a pretty impressive group. Hiro Uzawa was the first lecturer, then Bengt Holmström, then Partha Dasgupta, then Daniel Kahneman, and last year Alvin Roth. So we're on a roll, and fortunately we're continuing on that roll this year with Drew Fudenberg. Drew is one of the leading economists in the world, particularly known for his work in game theory, both pure game theory and applications, particularly to I/O, to bargaining, to contract theory. And he's especially famous for work on dynamics, so repeated games, learning, reputation, all of the topics that the summer school has touched on this summer have been impressed by Drew's work. He was an undergraduate at Harvard, graduate student at MIT. His first job was at Berkeley, then he moved to MIT, and now I'm happy to say that he's my colleague at Harvard. And one thing that I'm especially proud of is that he was one of my first students. So it's a great personal privilege for me to hand the microphone over to him. Drew Fudenberg.
I think I don't need it. Thank you, Eric, and I really mean that. It's a great honor to give the Arrow lecture. I've been awed and amazed by Ken's work for a long time now, and even still I'm discovering papers of his, important papers that I hadn't known about, and it's quite the record. He's also a very nice person to talk to. He's friendly, not arrogant, not pretentious. So I can't imagine of anyone I'd rather give a talk for than Ken Arrow. So thanks very much. Before I actually start the talk, in view of the content of a talk, I thought it'd be appropriate just to take a moment in memory of John Nash, who we lost this year. And you'll see the connection in the talk. So Eric asked me to prepare a talk with as little notation as possible, and he suggested I should not assume that people had heard of Nash Equilibrium. So I thought, well, if people hadn't heard of Nash Equilibrium, they probably haven't heard so much of game theory. So I'm going to start back at the beginning with sort of the prehistory of game theory and cover some basic definitions and concepts, and then proceed quite briskly and very informally towards the research frontier, hopefully without losing too many of you in the process, but we'll see. So games, what are games? They're interdependent decisions, settings where one agent's payoff can depend on what other agents do. And in these settings, what an agent wants to do might depend on what they think other agents will do. Okay? So the questions we have about games, how to predict what will happen in a game. Well, the standard procedure in economics and most other applications of game theory is to use equilibrium analysis. So the methodology is to identify the outcome of the game, the thing we'd like to predict or understand, with the set of equilibria, and specifically the set of Nash equilibria, or perhaps some subset of the Nash equilibria of the game. And the question I'm going to talk about today is when and why do we expect what we're going to observe in the game to actually look like the Nash equilibria, or perhaps some other set of equilibria. Learning in games part of a title, this is the idea that the reason we expect equilibrium to occur is that will occur as the long-run outcome of some process of non-equilibrium learning or adaptation. I'm going to argue this helps explain how and when we'll see Nash equilibria in static simultaneous move games. And I'll tell you what those are in a few minutes too. It can also suggest in those games when there's multiple Nash equilibria, it may tell us some of the Nash equilibria seem more likely than others. On the other hand, when we move away from these static games to dynamic games, games that unfold over time, as in most of the games we've had at the summer school this week, learning theory is going to suggest that maybe other solution concepts than Nash equilibria might be a better guide to predicting what happens. So, introduction and review. Where did game theory start? Well, it's hard to say. How much reading between the lines do you want to do, and how much partial credit do you want to give people's arguments? Certainly by the time of Hume and Rousseau, you can find verbal descriptions of things that we'd call games. The stag hunt game of Rousseau, Hume's story of cows on the common. But the first formal analysis of what we'd call a game was Cournot in 1838, who studied a duopoly model. There's two firms in a market. Okay, so it's two firms. So that means it's not really sensible for a firm to think that its output has no impact at all on market price, the usual competitive equilibrium story. Okay, so how are the firms going to make their output decisions then? Well, what Cournot said is suppose that firm 1 and firm 2 simultaneously pick output levels. The price then adjusts to clear the market. Firms collect their revenue and pay the costs. So that's the game. And a Cournot equilibrium is a pair of outputs, one for firm 1 and one for firm 2. So each firm's output maximizes its profit, taking as given the output of the other firm. That's an equilibrium in the sense that neither firm has any incentive to change its output, holding fixed the output of the other. So, logical question, how might such an equilibrium arise? Well, Cournot had an answer for this. He proposed a dynamic adjustment process where firms took turns adjusting their outputs, and the steady states of his process corresponded to the equilibria that he defined. So intellectually, this was an important precursor of a learning theoretic interpretation of equilibrium. So Cournot is the mid-1800s. Following Cournot, a number of other games were analyzed, each with its own special case. And these are mostly games that are also looking at duopolies. For example, in Bertrand competition, there's again two firms in a market, but now instead of the firms simultaneously choosing outputs, they simultaneously choose prices. And then the consumers say how much they want to buy, and the firms commit to meeting all comers at the prices they named. It's a different game. The Bertrand equilibrium is then a situation where neither firm wants to change its price, holding fixed the price of the other. Skipping forward many years, the big event in the history of game theory was a book by von Neumann and Morgenstern in 1944, Theory of Games and Economic Behavior. It gave the first general definition of a game that subsumed all these earlier examples. It also introduced the idea of a, quote, strategy as a contingent plan. So in the Bertrand, Cournot, etc. models, firms were picking prices or quantities. They were real numbers. And in a general contingent plan setting, a strategy is a complicated contingent rule. If he does this, I'll do that. More about this in a bit. So this book was hugely important and ambitious. It played a key role in the development of game theory and mathematical social science. And Bob Alman the other day said von Neumann was the father of game theory and Oscar Morgenstern was the mother. That was the quote from class. A quote from their book. I said it was an ambitious book. We hope to establish that the typical problems of economic behavior become strictly identical with the mathematical notions of suitable games of strategy. So reduce all of social science to mathematics. It's ambitious. It's very influential. The thing I wanted to point out is they had a very different interpretation of game theory and of equilibrium than Cournot or Nash or myself. They saw game theory's task as providing, quote, mathematically complete principles which define, and this is their quote mark, rational behavior in a social economy. And they wanted their principles to have a unique, unambiguous prediction in any setting. Okay? So everything's going to be math, and in any game, there's an answer. So that's quite ambitious. And in two-player constant sum games, also known as two-player zero-sum games, the min-max solution does exactly what they were after. These constant sum games have the property that all outcomes are equally efficient. That's what it means to be constant sum. You know, as economists, we're always talking about, well, this is efficient, that's inefficient, we're pro-efficiency. So most of the games economists talk about are not constant sum. This is not the right domain for us. And in general, once we move away from constant sum games, this goal of unique prediction is too much to ask for. Okay, that's one of the problems with their approach. The other problem, from my viewpoint, is they wanted to get all their predictions just from the assumption of rational behavior. And the assumption of rational behavior, in fact, does very little to restrict the possible outcomes. And even common knowledge of rationality isn't enough to deliver the unique prediction that von Neumann and Morgenstern wanted. So as economists or social scientists looking at non-zero-sum games, we need some other way of predicting what will happen when we don't have access to the min-max solution. Well, enter Nash, who defined what we call Nash equilibrium. Nash equilibrium generalizes Cournot equilibrium and the subsequent equilibrium definitions of Bertrand and so on. So to define a Nash equilibrium of a game, I've got to tell you what a game is. Okay? A game in strategic form is given by the set of players. Guess who the players are, the feasible strategies for the players, what their choices are, and a payoff function. So I'm going to start off talking about static games where the strategies correspond to actions. So think of these as buttons on a computer keyboard, or if you've played the game Rochambeau, rock, scissors, paper, it's like saying rock or scissors or paper. In dynamic games, strategies are more complicated. We'll get to that. A strategy profile, that's a term of art, specifies a strategy for each player. So in rock, scissors, paper, one strategy profile would be player one plays rock and player two plays scissors. If you remember, rock beats scissors. The payoff function says for each player what their payoff is as a function of a strategy profile, who wins. Okay? And a Nash equilibrium is simply a strategy profile where no player can gain by changing their strategy, holding fixed the strategy of the others. So it's as if the players correctly forecast the play of the others. Though I should point out that Nash equilibrium can be applied to players who can't make forecasts, such as bacteria or even genes, a bit following up on McCall's point. So this correctly forecast is an interpretation. It's not part of a definition. It's a standard solution concept in economic studies of static games, and it's used in various regulatory settings. For example, U.S. merger guidelines make use of Nash equilibrium to say what will happen if the number of firms in the market changes due to a merger. Well, when is this a good assumption? When should we think the outcome we care about is given by Nash equilibrium? Consider the following game. And here I'll explain how the game is depicted. So by convention, player one picks rows, up or down, and player two picks columns, left or right. The entries in the matrix are the payoffs of the two players, with player one's payoff first. So if one goes up and two goes left, they both get 0. Here one gets 5, 2 gets 4, 1 gets 4, 2 gets 5, etc. So looking at this, we can see there's two pure strategy equilibria. Down left is an equilibrium, because if 2 changes, it gets worse, 1 changes, gets worse. And up right is a Nash equilibrium. But up left is not a Nash equilibrium, and down right is not a Nash equilibrium. So we can't mix and match pieces of equilibrium. We can't take player one's part of this equilibrium and player two's part of that equilibrium and put them together and have an equilibrium. So that means what happens when we play the game can only be in equilibrium if all the players' play corresponds to the same equilibrium. They have to somehow coordinate on the same equilibrium. And note also, this game has 2 Nash equilibriums, so there's not an obvious unique prediction here. Certainly the Nash equilibria aren't unique. We can also talk about mixed strategy profiles and mixed strategy equilibrium. Think of a mixed strategy profile as some player 1s play up and some play down. Some player 2s play left and some play right. So this game also has a mixed strategy Nash equilibrium. If half the player 2s play left and half the player 2s play right, the player 1s are indifferent. So some can play up, some can play down. They're all getting the same payoff, they're doing different things. So now let's suppose we're going to play this game right now in this room. There won't be time, but I've done this before. So let's take, say, the people on the two wings. You're all player 1s, and you're going to be picking up or left. The people in the up or down, excuse me, thank you. And the people in the center are player 2, you're picking left or right. And suppose that I'm going to pay you, I'm going to say, you pick your choice, and I'll look what all the people in the other team did, and I'll pay you that many shekels for each thing. So if you're player 1, you pick up, you get 0 for each 2 who plays left, 5 for each 2 who plays right. If you play down, you get 4 for each left and 0 for each right. So let's think for a second what you would do. Okay? And in thinking about what you do, you might want to guess what you think everyone else will do. Well, personally, I have no strong prediction about what would happen if we actually did this. But suppose we did do it, and we had assistants collect all the choices, which were written on pieces of paper, and we tabulated the results, and I announced them and paid you off, and had you play it again. Okay? And suppose we did it again and again. So I don't have a strong prediction what would happen the first time we did this, but I'm quite convinced if we did it even 4 or 5 times, we'd end up very close to everyone playing one of the 2 pure equilibria. I can't tell you which one, but I'm quite convinced we'll end up at one of them. Why? Because this has happened many times in the past. There's no theoretical reason for this, but this is what's always happened before. It's my guess of what will happen next time. Now, there's a lot of work looking at how game theory performs in laboratory settings, including some we've heard about this week. These are done a bit differently. They're most often done with what's called anonymous random matching. Instead of me matching your play with everyone in the other team and announcing it publicly, you have a bunch of subjects who are sitting at computer terminals, and they put their choice with a button on or mouse click on the computer terminal. They're only told what happens in their own match. They're randomly matched to someone else in the lab. They see what happens, and then, okay, next period, everyone gets rematched with someone else in the lab, and you play again and again. So you have less data each period. All you see is what's happened in your own experience. But there, too, empirically, we have the same prediction. If we do this enough times, we'll end up at one of the pure strategy Nash equilibria. It might take more repetitions, because each person is getting less information each period. Experimental play does converge to Nash equilibrium in a reasonable time frame in some games of interest to economists, including the Cournot duopoly game I led with, what are called voluntary contribution games, where we're each deciding how much to contribute to a common good. The beauty contest game, which some of you may have heard, it's been talked about a lot, where everyone picks a number and you win if you're closest to 2/3 the average. And the double auctions that are used to explain equilibrium prices. So, here's some example data. This is a paper by Lisa Westerlund and co-authors looking at the voluntary contribution game. These 2 lines correspond to 2 different treatments of the game, 2 different specifications of the payoff matrix. In each case, the Nash equilibrium was for everyone to play 3. And you see here, we sort of stayed near 3 the whole time. Here we started up at 4.5, but we're moving down to 3. So this is what I would call convergence to Nash equilibrium over time. This is data on the beauty contest game where the Nash equilibrium is to bid 0. And people didn't start at Nash equilibrium, they played repeatedly, and you see it's getting closer and closer to Nash equilibrium with experience. So there's some experimental confirmation, at least in some games, that we care about, learning leads to Nash equilibrium. But in other games of interest, play does not converge, at least over the length of time that we can see in the lab. You can always ask, how do we know what would happen if you ran it 1,000 more periods? Maybe it would converge. But if it's practical problems of how long keep in the lab, do we lose interest? So perhaps more on this later. So Nash understood equilibrium in exactly this way, as the long-run outcome of an adjustment process. He had a chapter in his thesis that explored this idea. And that's really the underlying theme of learning in games. This idea that Nash equilibrium or equilibrium of whatever kind comes from playing the game over and over. The implications of this are simplest in what I call static games. So static games are those where the strategies are just actions, like rock, scissors, paper, or Cournot, or all those games I was showing you, beauty contest game, pick a number. Okay? In those games, when should we expect the play to look like Nash? Well, it depends on the game and also on the way people learn. Now, if I knew the exact rule that everyone used, I would simply put that in my computer and simulate. Or more precisely, because people are different, I'd have to know the exact distribution of rules used by the relevant population. I have an answer. It turns out to be hard to pin down the exact rules that people use. But still, it's good to know more about this. The data is very noisy. It's hard to know. So theorists have mostly been studying stylized learning rules that are too simple to really fit the fine details well, but fit quote-unquote reasonably well and are, quote, plausible. Various adjustment processes have been analyzed with varying degrees of rationality assumed on the part of the agents. Tonight, I'm going to focus on a particular part of this literature, the part that uses what I call belief-based models. These are models where agents form expectations about what other people are doing and then pick their actions based on the expectations. So it's a sort of model probably most familiar to economists as opposed to, say, psychologists or biologists. There's different classes of models used in those areas. So kind of belief-based learning, how do people form their beliefs? So the assumption I'm going to put out as the base case is asymptotic empiricism. This is the idea that with a large enough data set, beliefs will come to resemble the data. Beliefs about what other people do converges to the time average of what you've seen them do in the past. Okay? In particular, that means that you might have a prior belief that people usually play left. If you play a lot, you see everyone's playing right, you update. And eventually, your beliefs look like the data and not your prior. So one explanation for this assumption is that if agents believe they face a fixed time-invariant distribution of opponent strategies, this asymptotic empiricism is a consequence of Bayesian updating. Fine, that's reassuring for theorists or people who are used to these sorts of models. How about the evidence? The evidence suggests this assumption fits in, quote, simple static games. Well, I'm not going to define simple, but I'll suggest some counterexamples in a bit, provided the aggregate distribution of play is approximately constant. So for example, if we have a population that's slowly converging to a steady state, so then the state's not really constant, but it's not moving so fast. So then, in some sense, assuming the world is constant isn't such a bad assumption, and that's exactly the case in the data when asymptotic empiricism does better. On the other hand, people do seem to reject this asymptotic empiricism if they're given sufficiently strong evidence that it's wrong. For example, suppose you're playing matching pennies. You're trying to pick heads and tails. And your opponents play, this is your data, heads, tails, heads, tails, heads, tails, heads, tails. So if you're just asymptotically empirical, you say, well, 50-50 heads and tails. But it's pretty tempting to look at this thing and say, gosh, he's alternating. I bet it's heads next time. Okay, so this is a simple enough cycle that people will tend to pick it up. So that's one drawback with this asymptotic empiricism. Another is that in some settings, people display what psychologists call recency bias. What does that mean? It means they overreact to their most recent data. Well, if you're always reacting a lot to yesterday, your beliefs can't be converging to the empirical distribution. You're not asymptotically empirical. How big a problem is this? Well, it seems to depend on the feedback structure, what the subjects are told when they play the game, how it's displayed on the screen, and what sort of computation aids, like a calculator or paper and pencil, that they're given. So it's sort of an open research question. When is recency bias a thing that we need to worry about, and when can it be ignored? So that's one building block of these models. The next building block is what I call passive learning. So the assumption that the agent's actions have no impact on their observations. You're just sitting back and learning. So active learning versus passive learning. Okay? In a static game, each time the game is played, you see the action of your opponent, which is the strategy of the opponent. And you may be told what other people do, but if so, it's independent of what you do. So the key point is that in this setting, you have no reason to change your play to gain more information. You'll see exactly the same signal today, no matter what you do. That's what I mean by passive learning. So this is a natural assumption in these static games, because you're seeing everything you want to see anyway. When we go to dynamic games, it's no longer the case. It's not the case that what you see is independent of what you do. And then this passive learning won't be a good assumption. But in static games, it's okay. So I've talked about belief. Before this slide or this slide?
No, this slide.
Okay, please.
Agents see the strategy played by their opponent.
Yes.
And they see strategies of other players as well.
Sure. So suppose, okay, think of a lab setting. There's 24 people in the lab,
Okay, I got
and
it.
yeah, or in a social setting, you know what's happening with this restaurant, but you know what happens at other restaurants you haven't been to by talking to people. So you get information from interactions you weren't part of. Is there other questions? So I talked about beliefs. Now, in a belief-based model, people form beliefs and pick actions. How do people use their beliefs to take their actions? And I'm going to assume here strategic myopia. People pick actions that maximizes their current expected payoff, given their beliefs about how other people play. So there's some implicit assumptions buried in this. One is that people either actually doing the calculation of expected payoffs right, or they're getting the feedback to work it out, so somehow they aren't trying to maximize payoffs and failing. Given their beliefs, they can maximize their payoffs well enough that this is a good assumption. Another part of this assumption is people don't change their play today to influence the future play of others. So I'm matched with Bob today. We're playing coordination game. I'm going to play whatever I think is good for me today. I'm not going to change my play so that Bob plays differently tomorrow, because I won't be matched with Bob tomorrow. I'm being matched with Eric or someone tomorrow. Okay? So that's implicit. And a final thing that's implicit is that the map from belief to action is deterministic, or close enough to deterministic we could ignore the stochastic component. Any stochastic components are minimal. And the result is that with these assumptions of asymptotic empiricism and strategic myopia, if it turns out that the population converges to playing the same thing over and over, that thing, that strategy profile, must be a Nash equilibrium. Why? If the aggregate play is constant, beliefs will come to look like that constant. And if that play wasn't Nash, someone would change their play. Note, this doesn't require that players know game theory. You can converge to Nash equilibrium without knowing game theory. No player must be individually computing equilibrium, just like people don't have to know general equilibrium theory to be part of a price-setting economy. Okay. Implicit in this argument for strategic myopia, I'm playing someone different each day. Now you say, how often do you play the exact same game with different people? Well, maybe not so often, but people also extrapolate between games. You say this game with Eric is like that game with Bob. I'll use my old data to help predict this. And they learn from other people. And history and culture can help coordinate expectations too. This is the gist of Schelling's theory of label salience. So when will play actually converge? And what equilibrium will it converge to? Well, we have two different games here. This game has three Nash equilibria. Up left, that's clear, down right, and a mixed equilibrium, half left, half right. Okay? But in this game, the 50-50 looks sort of unstable, just like it does in the coordination game. You think if somehow we got off to a bit more people in this quadrant, we'd be absorbed there. The right-hand game is matching pennies. It has no pure strategy Nash equilibrium. There is a mixed strategy equilibrium. Once again, 50-50 is for each player is a mixed equilibrium, but stability or instability of this is less obvious. Do we think play will converge to the mixed equilibrium in matching pennies? Well, the formal analysis would require I write down a formal model. That would take notation, at least one subscript. So I'm not going to do that. Just tell you verbally, the easiest way to work out the model is to assume there's only one agent on each side. Okay? Or that all the player ones get together and pool their beliefs. So it's effectively a single player one. And here the mixed equilibrium can be shown to be unstable in the coordination game and stable in matching pennies. This assumption of only one guy per side isn't consistent with strategic myopia. If it's really one guy per side, the people are playing a repeated game with each other. They're not playing many copies of a static game, they're playing a repeated game. So it's maybe a little disconcerting, this to use it here. Turns out so we'd rather look at this learning question with many player ones and many player twos, and then they probably have different information because I know what's happened in my matches, you know what's happened in your matches. If we're not exchanging notes, we believe different things. So it's a more complex system, but luckily similar results apply. Okay? On the other hand, there are games where the unique Nash equilibrium is unstable under the standard belief-based dynamics. It's not so clear what actually happens in these games, but there's some experimental evidence that play in these games cycles, does not converge. So what do we do then? Well, we can apply learning dynamics to make predictions without assuming we get to equilibrium. Complication is not always, but it's often hard to say things analytically there. We may need to use simulations to work out the consequences of these dynamics. So where are we so far? There's no reason to expect Nash equilibrium the first time people play a game, especially if it's unfamiliar. Remember those pictures I showed you with play starting off at 8 and converging down to 3. Okay? If play in a static game does converge to a long-run outcome, that outcome should be a Nash equilibrium. No presumption that play always converges. Some games, yes. Other games, maybe no. And now before I go on to dynamic games, just briefly mention some caveats and research issues, because Eric said always start with people knowing nothing, but also be nice to say about current research. So choice is often at least slightly stochastic, and in some games this makes a big difference. So we need better models of random choice and its implications for learning dynamics. So the first is currently an active research area. There's lots of people working on models of stochastic choice. We need some more work on the second, importing this new work into the learning and games literature. I said the strategic myopia assumes people can do the maximization. So in these matching penny games, coordination games, that was trivial. If our static game involves move by nature and people have to compute conditional probabilities, we have trouble. Because lots of subjects have grave difficulty computing conditional probabilities. And if people, fine. So then non-Nash equilibria can persist in games that involve working with probabilities. Okay? And again, the prevalence of these mistakes, just like with recency, depends on the feedback and computational aids provided. More research needed here too, both theoretically and experimentally. What sort of, settings are most like field settings? Will give us. And as I've said, we also need to better understand when recency bias arises. So you can maybe tell from the ending of each of these three things, more research. When I get back from Israel next week I'm writing my next grant proposal. So you see, this is the more research is needed, more research is needed. Okay. Third and final part of a talk. Extensive form games is the methodology economists use to study games with sequential or multiple moves. And here the strategies are complete contingent plans. It's no longer an action, but it's a plan you could hand off to a computer that says what you would do in any situation you could possibly be asked to move at. These situations are called information sets. The actions then you take can depend on the actions of others, but we can still think of players choosing their strategy simultaneously, write these complete contingent plans down and hand them off to a computer. And we can associate a unique strategic form with each extensive form. So here's an example of extensive form. In a game tree, player 1 is going to play up or down. Plays up, then 2 gets to move. That'll be a sort of dot or circle here. This is 2's node. 2 plays A or B. If 1 plays down, 2 plays C or D. So this is the extensive form. We derive a strategic form. What are the strategies? Well, 1 has 1 choice to move, 1 place to move, and 2 choices. 1 has 2 strategies, up or down. Player 2 has 2 situations to move, 2 information sets, and 2 choices each. So 4 choices possible. AC means if 1 plays up, I'll play A. If 1 plays down, I'll play C. AD, if 1 plays up, I'll play A. If 1 plays down, I'll play D. BC and BD. So we have a 2x4 matrix. Okay? The definition of Nash equilibrium applies word for word, unchanged, to a strategic form on the last page, to extensive games. It's a strategy profile where no player can gain by changing their strategy, holding fixed the strategy. Now here, not holding fixed the action, holding fixed the strategies of the others. So one doesn't hold fixed 2's actions, you hold fixed 2's contingent plan when one thinks about changing. But the long run outcome of learning depends on what people see when they play the game. And since player 1 only observes 2's action, he doesn't observe how 2 would have responded to an action that 1 did not play. So if 1 plays up, 1 sees whether 2 goes A or B. 1 doesn't see whether 2 goes C or D. And in that case, play can converge to a self-confirming equilibrium that is not a Nash equilibrium. Remind you of Nash equilibrium? It's a distribution of strategies where each player is maximizing given beliefs about opponent's strategies, and beliefs are correct. So self-confirming equilibrium, which I'll abbreviate SCE, keeps the first condition. People are maximizing payoff given beliefs. It relaxes the second. Instead of beliefs are correct, we say beliefs are consistent with what the player has seen. Okay? So the correct, quote, on the path of play, but incorrect otherwise. If 1 is always played up, 1 learns what 2 does when 1 plays up. 1 is never played down, 1 might have the wrong idea what 2 does when 1 plays down. He has no data, so how does he know that he's wrong? Why does learning lead to self-confirming equilibrium? Agents who played a strategy many times will learn what happens when they play it. With myopic agents, so purely myopic, you just care about each period, you play a static best response to their beliefs. Now some of the grad students will know about sort of bandit problems, if people are patient, maybe there's information value, you might want to experiment. But even if agents are somewhat patient, they will eventually stop experimenting once they have enough data and play a best response to their beliefs. Okay? Once you have a very big sample, 100 data points, there's not much value in, well, the first 100 times I played down, it was bad. Maybe this time it'll be good. So, okay.
So what's an SC, in your example, what are the SC?
I will show you some in a different example. It's a good question. You need to see some examples. I will show you some. Important. Self-confirming equilibrium reduces to Nash equilibrium in static games. Why? We require your beliefs are consistent with what you see. In a static game, your opponent's action is the strategy. When you see their action, you've learned the strategy. There's no scope for false beliefs. Or more formally, everything is on the path of play. If your beliefs are correct on the path of play, they're correct. I'm almost to the example Bob asked for. One more point. The definition of SCE lets a player use a different belief to rationalize each strategy that has positive probability. Okay? And these heterogeneous beliefs are important in many game theory experiments and also important in the field. And the following game is the simplest example of SCE with heterogeneous beliefs. Not the most interesting economically, it's trivial, but it's going to be simple. I'm going to show you a game where the following data rejects Nash equilibrium. Suppose half the time we see player 1 go out, half the time 1 goes in and 2 goes A. So it's this game. 1 can play in or out. Out ends the game. Payoffs 2 and 0. In, 2 gets to move, can have 3, 0 or 1, 0. Okay? So in terms of Nash equilibrium, it's a Nash equilibrium for all the player wants to go out. If we saw that data, okay, that's consistent with Nash. It'd be Nash equilibrium for all the player wants to go in and 2 to play A. But it's not a Nash equilibrium to have half the data points here and half the data points here. So I've actually seen experimental papers that said we support Nash equilibrium because if we look at all observations, 80% of them are one of a Nash equilibria. But that, a mixture over this and this rejects Nash equilibrium. It does not confirm Nash equilibrium. So what does it mean different actions are justified by different beliefs? 1 plays out thinking 2 plays B. 1 plays in thinking 2 plays A. 1 plays in, 2 plays A. This guy has the right beliefs. Nothing to explain. 1 plays out, 2 plays A. This guy has wrong beliefs. How does 1 have 2 beliefs? Is he schizophrenic? Well, no. There's a population of player 1s in the lab. And some of them are playing out and not learning what's going on. And some are playing in and learning what's going on. So that's one way that self-confirming equilibrium can differ from Nash. Now, you might worry that in the definition, I said only that play is consistent with your observations. And we're used to ideas of backwards induction, or I'm not going to cover this in the lecture really, but the word subgame perfect equilibrium will be familiar to the students. Rationalizable self-confirming equilibrium adds the restriction that players know the payoffs of their opponents, but we can still have a different answer than Nash equilibrium. For example, we can replace player 2's move here with a subgame where players 2 and 3 move simultaneously and play a coordination game. Then even if 1 knows 2's and 3's payoffs, suppose 1's always played out. So 2 and 3 have never played the coordination game. 1 has to guess, will 2 and 3 coordinate? And if so, on what outcome? 1 has no data. So how should 1 know how 2 and 3 are coordinating with no data? Okay, that's what this says. In analyzing experimental data, it's important to distinguish between play that is inconsistent with maximizing the agent's presumed utility function. So if your presumption is people like money, and you have a one-player game and say, do you want some money? Want $1 or 0? And they say, I'll take 0. Okay, well that rejects maximizing money. We want to distinguish that from data which isn't maximizing money if the subjects knew what was happening, what everyone was doing, but is in fact optimal play for some sensible beliefs people could have. So you want to distinguish, failures to optimize from optimizing with different beliefs. And for doing that, heterogeneous beliefs about off-path play are important. There are many extensive form experiments where you look at them, you see different people doing different things. How can it be? Well, all these things make sense for some beliefs people could have given the data that they themselves observed. So that's an important message for people analyzing extensive form experiments. And I argue that this is particularly important for experiments that are designed to emphasize behavioral or social preferences. Like people know the ultimatum game. You have $1, and it has to be divided between 1 and 2, and 1 makes 2 an offer, take it or leave it offer, and 2 says yes or no. Okay? And if 2 only likes money, 2 should accept anything. In practice, many 2s won't accept 1 penny if you offer them 1 penny of $1. Okay, so fine, that's been shown. But then, should we assume that player 1 can correctly forecast exactly which offers get accepted? That player 1s know, what kind of behavioral preferences the subjects of the lab have? Well, I think that's ridiculous, because as an experimenter, you bring people to the lab, you yourself don't know what the distribution of social preferences will be. So how could the subjects know this? So if people don't know it, why couldn't different player 1s have different beliefs about which offers are acceptable? So some player 1s offer 50-50, some offer 0.6, because they don't know exactly what the payoff maximizing offer is. Unitary SCE is a restriction of self-confirming that requires for each player role with a single belief. So all the player 1s get together and share information. All the player 2s get together. And this is a different example, answering Bob, a different way self-confirming differs from Nash. They can differ because 2 players might disagree about the play of a 3rd player. This can happen in games with non-trivial information sets. These things I haven't defined formally, but I'm going to show you one on the next slide. It'll look like a tree from before, but there'll be some dots. And the dots between these 2 nodes of player 3 will mean that player 3 does not know which node she is at. So here, the dashed line means when player 3 gets to move, 3 doesn't know if it's here, because player 1 went down, or if it's here, because 1 went across and 2 went down. Okay, so this is a 3-player game, and we have the payoffs for player 1, player 2, player 3. And player 1 and player 2, if we saw in the lab 1 playing across and 2 playing across, so 3 never was reached, that's the outcome of a self-confirming equilibrium, but it's not the outcome of a Nash equilibrium. Okay, and why not? Because Nash equilibrium, so first, why is it self-confirming? 1 can play down thinking that 2 plays right, because 1 is more than 0. Sorry, 1 can play across thinking that 3 plays right, because then 1 gets 1 versus 0. 2 can play down thinking 3 plays left, because 1 is more than 0. Okay? Here, 1 and 2 have different beliefs about player 3. We end up here. Cannot do this in a Nash equilibrium. Why not? In a Nash equilibrium, the beliefs of 1 and 2 must be correct. Okay? What does it mean correct? Well, I'm not going to say what 3 does, but the point is, it's only one way to be correct. So if the beliefs are correct, they're identical. And any common belief of 1 and 2 is going to make at least one of them want to play down and give 3 the move, because 1 wants to play down if the probability of left is more than a third. 2 wants to play down if the probability of right is more than a third. There has to be more than a third on one of those 2 things, so weights have to add up to 1. So this is not Nash. And note, I left ambiguous what player 3's payoffs were. Suppose the 1 and 2 knows 3's payoffs. Can't they then predict 3's play? Well, no, not if x and y have opposite signs, but now to predict 3's play, you have to know what 3 thinks who's giving 3 the move. So there's no way to predict 3's play from knowledge of the payoffs. Okay, so punchline, play needn't converge to Nash equilibrium. It can converge to self-confirming. However, this can't happen. We can't get stuck at these non-Nash outcomes if the players on the path of play learn what would happen if they deviated. So if we told 1 and 2 what 3 is doing, that kills this outcome. Many applications of game theory restrict attention to the subset of Nash equilibria that are called subgame perfect. This equilibrium concept implicitly supposes that beliefs are correct at every information set. Everywhere in the tree, people have correct beliefs because they're optimizing. What do we think will happen when people are learning in these games? Well, let's maintain this asymptotic empiricism. Beliefs look like the data. Use the law of large numbers. Suppose that somehow players 1 and 2 got an infinite number of observations, or a very large number of observations of player 3's play. If they get a large number of observations, then from the law of large numbers, their observations look like what 3 is doing. And from asymptotic empiricism, their beliefs look like the data. So their beliefs would end up being correct. Okay? So how could that happen? Well, if the people are not myopic, if they're now somewhat patient, they might choose to experiment. They might choose to play an action but does not maximize today's expected payoff to learn about the future. So I don't think this is a good idea. I'll do it one time just to see what happens. Okay, that's experimentation. How much experimentation will agents choose to do? And which information sets will they actually learn about? Well, suppose, here's a three-player game. Suppose one usually plays A, but at time t, with probably 1 over t, one plays B. And 2 usually plays D, but occasionally plays C. Okay? Well, 2 might like to learn what 3 is doing. 2 could learn what 3 is doing by playing this way a lot. But if 2's only being reached with probably 1 over t, 2's not really being reached so terribly often. Is it in 2's interest to experiment when 2 hardly ever gets to move? To answer that, we need a model. I can't write down the model. I can verbally describe the model. Suppose people are patient and are maximizing the expected payoff. There, that's the model. Okay? I'm going to argue that then, if these people are not just a little patient, but very, very patient, that learning with patient players leads to Nash equilibrium. In the sense that patience enough patience gets rid of all these self-confirming equilibria that aren't Nash. Why? If a profile is not Nash, there must be someone who's moving on the path of play who could do better by deviating. That's what it means not to be Nash. You can gain by changing your play. If you really have a gain from deviating, and you experiment, you'll get some data. So it's noisy data. It could be misleading, but it's unlikely to really convince you that you have a zero gain from deviating when you have a big gain from deviating. So patient players will keep on experimenting. Patient players will keep on experimenting as long as they believe this probability of a profitable deviation is non-zero, because you're paying a one-time cost and you might get a long gain and you're very patient. So if agents are patient and they really would do better by deviating, they're likely to learn it. So this is a verbal intuition for why this statement is true. The converse of a statement is false. It's not the case that all Nash equilibria can be long-run outcomes. People will learn so much that some Nash outcomes can be ruled out. Okay. Just which of these equilibria can be ruled out depends on how much agents learn about play two or more nodes off the path of play. I'm getting a bit jargony. And thus on how much experimenting agents do at off-path information sets. So the answer to this question with patient players is only known for simple games. These are games of perfect information. So there are no little dashed lines. Every information set's a singleton, where no player moves more than once on any path. So I'm going to close with a little bit of formalism. No notation, but definition. We'll say that a node of a game tree, of a simple game, is one step off the path of a strategy profile if it's an immediate successor of a node that is reached with positive probability. So if no one deviates, it's not reached, but someone who's being reached on the path of play could deviate and make this node be reached. And a strategy profile is a subgame confirmed equilibrium if it's Nash, and if moreover, at the nodes one step off the path, the continuation play is self-confirming. That's a definition. And the theorem is that in these simple games, any pure strategy subgame confirmed equilibrium can be supported as a limit with patient learners. These are things that are robust to lots and lots of learning. Why? People are on the path, they're very patient. They have a reason to experiment. If they learn they could gain by deviating, that's a potential big payoff. I'll use that information every day. The players who are one step off the path may not ever experiment, because they're only reached if people on the path experiment, and that's not happening so often. So people one step off the path need an experiment. So they don't learn what happens 2 steps off the path. But even if you're 1 step off the path, you learn what happens if you don't experiment. So looking back at this picture, so suppose that 1 experiments with B. Okay? So 2 is reached infinitely often. 1 learns 2's play. Suppose that 2 now, instead of what's written here, 2 says, I'm not experimenting because I hardly ever get to play. I think this is good. I'm going here. I'm not going to learn 3's play. If I had put in, or just change it around and say, yeah, fine. Let's put in a move for 3 here. 2 would learn what happens here by 3, but not here. So so player 2 will learn what happens if 2 does not deviate. So we have some control on 2's play, but it's not the full power of subgame perfect equilibrium. So this theorem, we claim, may help explain the apparent durability of one of the laws of Hammurabi. So this civilization endured for a long time. They left these massive stone steles, and they had with the laws engraved on a stele. So presumably, if they took the trouble to write these things down, they had some durability. So here's a translation. It's not ours. I can't tell you who translated this, of one of the codes. If anyone bring an accusation against a man, and the accused go to the river and leap into the river, if he sink into the river, his accuser shall take possession of his house. But if the river prove the accused is not guilty and he escapes unhurt, then he who brought the accusation shall be put to death, while he who leaped in the river shall take possession of the house that had belonged to his accuser. So they took the time to hire scribes to etch this into some stone. What are they thinking? Well, one thing, it suggests they were worried about an incentive problem. They wanted to prevent false accusations. Suppose there's a crime that's been committed and the police think you saw what happened. You have this noisy upstairs neighbor. Wouldn't it be nice if your noisy upstairs neighbor went away? So maybe you'll accuse them instead of the guilty persons. So they're trying to give an incentive against false accusations. But this seems to rely on what I call a superstition, a false belief. It seems to rely on the belief that the guilty are more likely to drown than the innocent. That's what it takes to hold this thing together. Well, so people are superstitious. That makes life easy for law enforcement. But if people are superstitious, they could have saved money on scribes and used a smaller piece of stone with a much simpler code. Anyone who commits a crime, God strikes them dead by lightning. Okay, very pithy, short code. The wrong belief in the lightning strike superstition is 1 step off the path. Anyone could commit a crime. No lightning. Okay, so it's not robust to learning by patient players. Because I said, if people are patient, anyone on the path who could gain by deviating would learn that they should deviate and the thing crumbles. But in this trial by river superstition, the wrong belief is 2 steps off the path. If the accusers believe the superstition and accuse truthfully, then the criminals optimally don't commit crimes. The criminals don't have a false belief. The only one with the wrong belief is the accusers. Okay, the accusers only get to act when a crime is committed. So if there's not much crime and you're asked as a witness, there's not much point in making false accusation. Now this model, like any model, is very stark. We left things out. You could say, well, in our model, the only time crime gets committed is someone decides to do it as an experiment. There could be other sources of crime. Maybe the payoff to crime is stochastic. And sometimes crime really is worth the fine, the punishment. It's worth committing the crime. Or maybe people might commit crimes by mistake. So there's some background level of crimes. But still, if the probability of crime is, for whatever reason, is low, the probability of being called as a witness is low. So then the reason to experiment with false accusations is low because you're a witness now, you won't be a witness again for a long time because there's just so few trials. Now in the US, most people are not even called as a witness once in a lifetime. Maybe the same was true in Babylonia. That might help explain this superstition. So conclusions, equilibrium in games might arise quickly, slowly, or not at all, depending on the nature of the game. if the players directly observe each other's strategies, then when play converges to repeatedly playing the same thing, that thing should be a Nash equilibrium. If players don't observe opponents' strategies, because they're playing an extensive form game, then incorrect beliefs and self-confirming equilibrium may persist. So in the model, forever, more realistically, for a long time, over a relevant time frame. We get tighter predictions, smaller sets of stable outcomes if players are patient, because then they do more experimenting. People on the path learn about any possible deviations. People one step off the path at least learn the continuation play. So thank you very much, and ta-da. So I don't know the schedule. Is there time for a few questions before we go?
Why don't we have a few questions?
Wonderful.
Long questions is wrong, you can read them.
Yeah. No, only theoretical questions, no experimental questions right now. Please.
How dependent is this on the learning rate of the different players? If one player is kind of learning the belief very rapidly and another is learning very slowly, you get kind of differences.
So you sound like you're talking about only two people. Can I think about two populations? So the stability of some outcomes can be affected if one side learns much quicker than another. So for some of these, yeah, so if it's a systematic difference in the learning rates, that would matter. That's fair.
Now, how much is known about?
Very little. There's examples for particular dynamics in particular games by playing with things. I don't know of anything general on that.
Though learning is converged.
Very good. Okay, thank you.
Just
Oh, please.
before,
Yeah.
1 minute.
Please.
We have a tradition in which the speakers,
Yeah.
the aero lecturer, sign on the posters and the director. So if you
Yeah.
and one is directly for you.
Okay.
And
Yeah.
so
Okay. So
you'll sign.
any
You'll sign
so where? I'm sorry. What's the? Is there?
whatever you want.
No. What's
Yeah,
what's the
that's
norm?
a good one. No, it will change the balance. So,
What should I sign?
Yeah, just
Oh, how about
here. So
there? Is that-
okay, sounds good.
Perfect. Okay.
And we have a small token for you
Oh.
as well. So
Oh.
please
Ta-da.
enjoy.
Ta-da, Rebbe.
And, thank you very much. This is well done.
Oh, thank you.
Excellent,
It's-
really.
It's a challenge to use no notation and try and do something.
Fantastic, fantastic.